Hello everyone. Today I'll be presenting our work on a caching management system over the cloud that considers object sharing. So let's consider a simple system that consists of a database and a caching unit, as illustrated on the right side of the slide. These two are typically placed in a single data center or in a single region. Then on the other side we have multiple web servers. I will also refer to them as edge servers, and they can be in different geographical sites. And then furthermore, what we want to consider is a setting where different edge servers can have different allocations of cache. And you can think of this as different tenants paying for different amounts of cache sizes. So the question is, why do we want to consider a system with such setting? Well, let us consider a virtual reality application where the system architecture is as follows. So on one end of the architecture, we have the database located in a data center. And then on the other end, we have a pool of VR users that connect to different proxies. And it's important to note here that the proxies are financially separate. And an example of such proxies could be schools, and where the VR users are the students that are attending to that school. And then lastly, we have the edge cloud, in which the content of the VR application is stored and it is shared between the proxies. The goal is to develop a system in which different proxies can pay for different sizes of caches. So how can we build such system? One method of doing so is to have a dedicated caching instance for each proxy. And there are two properties that we need to consider in this design. So the first thing is that this design provides an isolation guarantee between proxies. And what I mean by this is that no user should receive less cache space than what they're paying for. However, in such design, we can have multiple copies of the same object in different instances, especially if we consider a workload that are highly skewed in terms of popularity. And then another design is to allow for multiple LRUs to share the cache instance. And in such design, we can minimize the number of copies in the cache. However, we have yet to address the former property, which is how to provide the isolation guarantee. So for this work, we implement an LRU framework where it considers the following. It considers a system with paying proxies for cache allocations, as we've mentioned before. And the key idea is that the size of the object is divided equally among the shared proxies. So now let us modify memcached to enable object sharing and allow also for multiple allocations of different cache sizes, as we have discussed. To do so, we're going to have multiple LRU lists categorized into two parts. So each LRU on the left is mapped to a single proxy. And then we have the block with a thicker border line in the middle, this one right here, and it's divided into different slabs. Each slab is identified with a class based off the maximum size of each of its elements. Here I color code the slab classes, where blue is the small size items, red is the medium size, and green is the large size. And then on the right side, we have these LRU lists, and these are associated to the slabs. These are used to evict from a slab if it was full, and that we cannot allocate a new slab with the same slab class for the new object. To save some space in the slide, I want to get rid of the proxies in the figure, and then let's add some details that we're going to need to present the current state of the system. So in the bottom left table, it represents the state of each of the proxy LRU, and what it essentially describes is the availability of cache space for the different proxies. And then on the bottom right table, it represents the state of items that is in memory. And that table consists of the actual size of the object, the degree of sharing, and therefore calculating the virtual length. And then the bar graph that is in the top right is just a visualization of the last table that I have described. So what happens when a GET request is received? In this example, let's say that the second proxy sends a GET request for item 1 with a medium size. Using the native memcached hash table, we can access the item in the slab in almost big O of 1. And then what we do is that we update both of the LRU lists before returning the value. So one important thing to notice is that the virtual size of the items are not affected basically by GET request. And then I want to do the same thing with the set command, but before actually describing the set command under MCDOS, I want to clear up some terminologies that we're going to use. The first term is that the term inflation. It is defined as the increase in object's virtual size due to an eviction. In other words, the degree of sharing has decreased. Looking at this time series of figures, we see that the insert of object 1 and LRU1 has caused a violation in terms of the space allocated for LRU1. Hence, an eviction of the tail object is needed, which is in this case object 2. This eviction caused an increase in the virtual size for object 2, hence we use the word inflation, and then as a result a violation in terms of the space allocated for LRU2, causing another eviction in LRU2, and so on and so forth. And we can see that there's an effective series of eviction, which leads me into introducing a phrase, ripple effect. And ripple effect is the series of evictions and LRUs when executing a set command. And we also use the phrase ripple length to describe the number of evictions that have occurred after a set command is executed. And then we have the last term that I want to introduce is deflation, which you might have guessed at this point is that it's the decrease in the virtual length of an object due to increasing the degree of sharing. And an example here is that we have an object 1, insert an LRU1, hence the degree of sharing has increased, and then causing the virtual length of the object to decrease. So given this state, if we get a so let's say again that we receive a request from proxy 2, and we find that the set request is for a new key in the system, hence a new allocation for the item is needed. And by looking at the bottom left of the table, an eviction will certainly happen since there's no available size to accommodate for this object, and it can potentially cause a ripple effect. And then instead of going through step by step, let's assume that we have performed all the necessary steps, and that the space allocations are respected for the LRUs that is mapped to the proxies. And we can notice that the eviction in LRU2 have caused other evictions in other LRUs, which I refer to as ripple effect. And in this case, it actually caused a ripple length of 6. We find that there are objects that were deallocated from physical memory, and this is due to it not being shared anymore across the LRUs. In other words, they have a sharing degree of 0. So given MCDOS, we run our experiments on AWS and calculate the hit rates for each object. We find that we give an accurate working set approximation for the cache hit probabilities of the cache with object sharing system. You can see that there are vertically 2 sets of results. Each of these sets represent an LRU model that is used in the native memcached. So the flat LRU and the segmented LRU. Due to the time constraint, you can find the details of these 2 models in the memcached documentation website. In our experiments, we found an improvement to 2 to 3% on some of the popular objects under the segmented LRU. Also, as I mentioned before, a ripple effect can cause sometime a huge overhead. So we run our experiments with many clients with different distribution of the request, and we evaluate the ripple length and its effects on the latency for set request. So in conclusion, to summarize this talk, we considered an LRU framework that supports object sharing. In the Edge Cloud, we provide a working set approximation of the hit probabilities. We implemented the native memcached segmented LRU and MCDOS, And lastly, as future work, we are evaluating ways in which to reduce the ripple effect overhead.